In a histogram, the areas of the blocks represent percentages, O may be relative frequencies, right? So most of the times people use show percentage histograms, but when you come to something later on, something called probability density functions and so on, actually more accurate thing to look at is the relative frequency, so that the total area is equal to 1, right? Percentage histogram total area is equal to 100. Later on, when we talk about probability density functions and so on, those are some curves, smooth curves of the relative frequency histogram, right? So you find out the density so that the area is equal to the relative frequency, not the percentage. But the shape, of course, is the same for both. So there should not be gaps in histogram. So after that, how to calculate, how to find out the height is. So the height is actually the density, we call it the density generally. So here the book says it's showing the crowding, right? Crowding is also the same as density, right? How much crowd in a certain unit area. Right. So here we look at two situations where histogram was useful in some analysis. Both are coming from book examples. In one example, histogram is used to find out whether there is an association between two variables. Especially to find out whether there is an association between a categorical variable and a quantitative variable. Right? One qualitative and one quantitative variable. So, what do you mean by there is an association between that kind of two variables, right? For example, whether one might ask whether height is associated with the gender. Right? Height is a quantitative variable, gender is a qualitative variable. Is there an association between height and gender? Is one possible question. Right? So, when would you say that there is an association and when would you say there is no association? We can actually answer that question by looking at the distribution of height separately for both groups. Right? We can look at the distribution of height for men and distribution of height for women. Right? So we would say there is an association between height and gender if these two distributions are somewhat different, right? Otherwise, if they are the same distribution, then that means there is no association. The distribution doesn't change with the gender. Distribution of height doesn't change with the gender, means there is no association. If the distribution of height for male and distribution of height for female are different, that means there is some association. So we will use that idea to check whether there is an association, and if there is an association, whether that can be considered as somewhat causation. Of course, in an observational study, you will never be able to prove some association is causation, but by checking some criteria that I mentioned in the last week, probably we can get some hint whether that is more probable to be a causation and so on. So this example talks about, they wanted to check whether there is an association between blood pressure and some birth control, taking birth control pill in women. Right? Two groups were compared, some women who used birth control, oral contraceptives pill, and who didn't use that. Right? So that was the question, whether there is an association between the blood pressure and the usage of this particular contraceptive pill. The main question was whether it is affected, that means whether there is a causation, but of course this was an observational study, therefore we cannot prove any causation even if there is one, but we can see whether there is a highly likely possibility to be a causation. So these are the data. Actually, these data were generated, created by me. because they had given a separate data file for different ages, I think. No, actually, I just only combine it. So these blood pressures are given as some intervals for users and non-users. These are the frequencies and these are the percentages. So the first thing one would do is actually they will look at this distribution, percentage distribution, and this percentage distribution. Of course, the widths of these intervals are not the same, therefore, and the blood pressure is a continuous variable. So we can look at actually histograms, percentage histogram. Right? In the histogram, they have to adjust for the different widths. So if you do that, this is the graph. Well, are these the same? Actually, here they are the same length, right? Yeah. Even though you have same length, you have to prepare a histogram. In that case, this axis is the density. In this case, I have prepared those two percentage histograms. What can you say? Right? This blue histogram is the non-users, the red one is the users. Of course, no matter how close they are, even if really the distributions are the same in the population, if you look at, you can draw these histograms. If you have the data for the whole population, you can draw that. No? So assume that, for example, you draw that for the two populations of men and women, and even if the distributions in the populations are exactly the same, when you get a sample, of course, the distributions can be slightly different. Right? So you can see that there is some difference. Right? So just because there is some difference, we will not say always, because here we are looking at these things, we want to talk about the association in the population. We are always interested in population properties. Right? So by looking at these ones, you want to see in the population whether the pressure depends on the using or non-using that drug. Right? So of course sample histograms will be different even if the population histograms are actually the same. That is something that we have to remember. Right? So here this is actually two sample histograms. Sample histograms definitely looks like they are not the same, very clear. The question is, are they different enough as to decide that the population quantities are different? Right. So how do we look at it? Actually, there are some mathematical methods to check whether these sample distributions indicate whether the population distributions are different or not. We are not going to that part here, but that is what we call the inference usually. By looking at the sample things, there are something called statistical test, hypothesis test. We check, do those tests to decide whether this difference that we see here is enough for us to decide that they are different in the population also. That's what you usually do at the end. But here, just by looking at the sample quantities, we would say that the population quantities are more likely to be different if there is a systematic difference here. If there's, of course, there's a difference here, but now we will see whether the difference is kind of systematic or not. If the difference is kind of random difference, then that may indicate probably the population may still be the same. The population distribution may be the same. But in the sample also, we will see some kind of systematic difference. That may be a more indication that the distributions are different in the population also. Right? So what do you mean by a systematic difference? If you look at these two graphs, you will see that before, from up to here, right, up to this point, this blue histogram is always above the red one. And after that, red one is always above the blue one. So that's a kind of systematic difference. Right? But otherwise, for example, here, for example, in some parts this was above this and some parts this was below that, and the other side also like that. That is kind of a random difference. Right? But here there is a systematic difference. So therefore, one might say, okay, therefore that indicates that the two distributions in the population also more likely to be different, and therefore that indicates a possible association between using pill, using or not using pill with the blood pressure. So that's how you argue about it. Right? Because there is a systematic difference between the two distributions of blood pressure for the users and non-users. That is an indication, probably, an association between blood pressure and usage of pill. But you have to be careful. You can come to that kind of decision only because this is an observational study here. We have an observational study. Right. There is a direct association. We can conclude that there is a direct association only if there are no other variables which affect the. There are no other variables which affect the blood pressure. In other words, if the two groups are different only by whether they are taking pills or not, with respect to if there is any other variable which affect blood pressure, suppose they are similar with respect to those variables, then we could, for example, if you see this kind of two graphs, then one might say, okay, there is an association between these two variables. There is a real association. But the two groups are different with respect to some other variables also which can cause differences in blood pressure, then we cannot come to the decision that there is a direct association. Right? So actually in this case also we have at least one, we may be able to think of some other variables, at least one variable which is a possible confounder here, that means another variable which is related to the blood pressure as well as whether they are using pill or not. Right? That kind of variable is called a confounding variable. Age of the people. Right? Now they saw that in this particular two samples, now we know generally also, those who take birth control pills are if you consider that population of women who are taking birth control pills, those are the people who probably expect in the childbearing age, right? All women would not take this thing because they are not in the childbearing age, right? So they saw that in the group of the population of users, there are more young people than older people. The other group, more older people than young people. So with respect to the age distribution, of course, then these two groups are completely different. Not completely, but somewhat different. Right? But we also know that blood pressure is associated with age. Usually blood pressure goes up when the age goes up. Right? Older people have high blood pressure usually, and young people don't have. Right? So age and whether they are taking pill or not is associated because those who are taking pill, more young people, the other group more older people. So age is associated in that way with taking pill or not taking pill. On the other hand, age is associated with blood pressure also. So therefore age is a confounding variable between these two variables of between the association between whether they are taking pill or not and the pressure. Right? So therefore, just by looking at this graph, therefore we cannot actually decide whether there is a real association or not. Right? Probably the seeming apparent relationship here, the two different distributions may have, of course, not because of the pill, maybe probably some other variable like age, or maybe some other variable that we have not thought about. There may be some other variables. Right? So therefore, the apparent relationship here with the pill usage may not be a real association. So if you were to check whether there is a real association or not, what do you have to do now?
Make the groups seem as possible.
Yeah, now you have to somehow stratify with the age, right? Look at the people with the same age, these two groups. So,
age doesn't affect these two.
age doesn't affect what?
Uh,
Taking this thing up? then
Yeah.
taking pill or not? No, age it affects no. Because more young people are taking pill and more old people are not taking
Yes,
pill.
sir. You said that the young people are low blood pressure than the old people, so this is
So that's what you mean by confounding, right? It's mixed, right? Mixed, we cannot separate them. Young people are taking the pill, young people have less blood pressure also. Old people are not taking the pill, most of, and they are having high blood pressure also. So whatever the effect of taking pill or not, and the age, they have mixed effect on the blood pressure. So we cannot separate and see the effect is only from the pill.
yes, sir. But if we consider that the pill doesn't increase the blood pressure, the graph should be the other way around, right?
But we don't know no, whether a pill is affecting or not. That's what we are trying to find out. No? We are trying to find out whether the pill is affecting or not.
You're saying effects cancels out.
No, effect doesn't cancel out because the effect cancel out. What we want is the age effect to be cancelled out. But the age effect doesn't cancel out here. In one group, there are more young people than the old people. The other group, there are more old people than young. So age doesn't cancel out. But if you consider two groups where the age distribution is the same in both groups, then at the end age effect will be cancelled out. So that's what you have to do. Somehow you have to stratify by age. Within that group, then you have to consider those who are using the pill and those who are not using the pill, and we can look at their distributions of pressure. So when you compare, they are roughly the same age, you know, both. So in that case, if there is a difference, probably that difference is due to a pill, not because of the age, because we are considering the same age. So that's what we have to do actually. Right? So that's what they did later on. They had this data for different ages. They are not exactly 1 year, but age group, but roughly the same age group, at 70 to 24. So there's not much. So therefore, they looked at the users and non-users. For example, for this set of people. Right? For example, they consider all the women who are taking pill and not people, but in this age group only. Right? So now if you look at the distribution of these numbers and distribution of these numbers, then if there is a difference, then that is more likely to be due to the taking the pill or not taking the pill rather than due to age, because roughly their age is the same. And you can do the same thing for this group also. Again, two graphs for users and non-users, but for these people and these people. So they have shown one graph only, right? So these are the two histograms of blood pressure for users and non-users in 25 to 34 age group. So roughly one age group. So within that we can see that okay, they are roughly the same blood pressure due to age. If there is any difference, probably mostly that difference is due to pill, if somebody doesn't come up with some other possible confounder. So we have to think whether there are other possibilities, of course, before we conclude that maybe this is a highly a causation. But at the moment they are considering only age. So in this picture also we see the same phenomenon that we saw in the original one. When you put all the people together. Right? Again, one distribution is always above the other in one part. The other distribution is always above the other in the other part. So still there is a systematic difference. Right? So now this systematic difference probably indicate that in the population these two distributions are different, and therefore now that difference probably is due to, more likely to be due to pill usage rather than age now, because the age is the same, almost the same in both groups. Right? So that's what they decided actually. They looked at the other age groups also. I don't have the picture for that. But later on, once they control for, we say we control for age, we look at the association after controlling age, that's what we call, that's how we say it. Keeping age fixed as much as possible, we look at the relationship. So after controlling for age, they saw still the previous or some difference, right? Some systematic difference exists in the two distributions. So that indicates with high probability or more likely that there is an actual association between pill usage and blood pressure. Right. So once you decide that, actually later on they found out some other theoretical reasons also. There are some other things that you have to check, so like time effect and so on. So with those things they decided actually this is a real effect, right? With more evidence, theoretical and so on, logical reasoning, they decided that actually there is a association, real association between the blood pressure and whether they are taking pill or not, pill usage. So then the question, if there is a real association, what is that association? How much is the association? What is the difference? How much difference is caused by the pill? That is a reasonable question to ask. If there is some kind of difference, what is the difference? So, in order to answer that thing, what they have done in the book is actually they try to, for example, if you push this to the right, you will see that, if you imagine, for example, we can actually do that later on. If you imagine that push this means if you add some amount, some value, the same value to all the blood pressures of non-users, then this histogram will be pushed to this side to some extent. So if you push this thing so that it will be roughly the same, not exactly, but there will be no systematic difference, still there will be some difference, but that difference will look like a random difference. Then you can find out how much you have to push or how much you have to add to the blood pressure of non-users so that you will have roughly the same distribution. In that way, you might be able to identify the real difference. So by doing that, they found out that if you add about 5 to each blood pressure of non-users, this will shift to this side so that after that the two distributions will look like this. If you add 5 to 5 millimeters to every value for the non-users, the two histograms will look like this. It's only shifting the whole distribution. Right. And you can see now that there is a difference, of course, but the difference is not a systematic one like earlier. It's a random one. For example, here this is above, but here this is below, this is above, this is below, and so on. So it's not a real difference, even though it's a difference. It may be even a random difference. So therefore, people decided that more likely, it's not actually a real causation decision, but it's more likely that the pill increases the blood pressure about by 5 millimeters. Right. So that means the blood pressure of non-users plus 5 is equal to the blood pressure of users. Blood pressure of users is equal to blood pressure of, on average. Right? Not everybody is like that, but on average. So that was the conclusion they came. Right? But still, we cannot say it is happening mathematically like this. That's why I put a question mark. It's not a real causation or something, but it's more likely. Right? There is a real association, and the pill is causing about 5 millimeter shift to the positive side, or increasing the blood pressure by 5 units. So that is the decision they came. Right. So after controlling for the confounder, that is age, histograms are effective. Right. Now the topic of our chapter is histogram. So why are we considering here something else? Like here they are actually using these histograms to decide whether there is an association or not by looking at the distributions of blood pressure in the two groups. So histogram was used, so that can be considered as the usage of the histogram. Right? So after controlling for age, you can look at the distributions, histograms of the pressure, and then by comparing those, we have come to the lesion. That is one example in the book. Another example they have shown is they call it selective breeding example. Selective breeding. So this is the scenario there. In 1927, the psychologist Spearson introduced an idea that test scores of intellectual abilities like reading, comprehension, arithmetic, or spatial perception were weighted sums of two independent components. Right? So this person came up with a kind of a conjecture or theory saying that the test scores are made of two things with a weight. So they said it's a weighted sum of two independent components. That means some number times one component plus another number times another component. Where one component he mentioned it called general intelligence factor, denoted by G, and the other is called the ability factor. So that was a theory or kind of idea came up by this person Spearman. He's a very famous person actually. There are some measures also about correlation, Spearman's correlation coefficient and so on. So because he's a well-known person, everybody was not refusing his idea directly, but some people were skeptical, and therefore they ran out some experiments, not using people but using animals. Right? So this person was speculating about people, but some people did some experiments with animals. So one person was somebody called Tyrone, decided to check the theory on animal population, where it is simpler to control extraneous variables. One reason, of course, doing experiments with animals is easy because we can control all the other factors. Right? Only we can have the same age animals, and all the other factors can be controlled to most extent. Only the treatment will be different. Right? But with the people, it's not easy to do that. So therefore, doing experiments with animals is easier. Tyrone used rats, which are easy to breed in the laboratory. To test their intelligence, he put the rats into a maze. Right? When they ran the maze, the rats made errors. Right? So you start with somebody and some place, and they have to go to a certain end. Some rats were able to go to that end through the maze. Some were not able. So he counted, he did this experiment with how many mazes? 19 runs. Right? So for each rat, they had to be exposed to 19 times to the same maze. So if you take, for example, one rat, he may have made, out of 19 trials, he may have made 5 errors. All the other times it was successful. Like that, for each rat, he counted the number of errors made by each rat. So that means fewer rats. If some rat is making fewer rat, he is considered as a kind of a intelligent rat. The other ones are not like that. So few errors means we call them maze bright. At least for that maze they are bright, right? And more errors means maze dull. That's how they name it. So different animals, there were altogether 142 rats. Each rat was exposed to 19 trials. So for all these 42 rats, they have a number, right? Number of errors made by each rat. So 142 numbers. So when they drew the histogram, they had generally this shape. Here what you have is not actually histogram. This is a smooth histogram giving the shape. So what does it tell you? this can be considered as, for example, percentage density or frequency density, but these are the number of errors. So you can see that most of the animals with the high percent density made errors between 0 and maybe 75 or so, but there were few animals with large number of errors also. Large number of errors, like two. Yeah, because there are 19 these things. So if you, for example, every time he made errors, then his number of errors to be 200. This is something I didn't understand. It cannot be 200, no? If one rat ran for only 19 these things, the number of errors has to be 19 or less. So it is the total. What is this? Number of errors. To test their intelligence, he put the rats into a maze. When they ran the maze, the rats made errors by going into blind alleys. The test consisted of 19 runs through the maze. The animal's intelligence score was the total number of errors it made. So the bright rats are the ones with low scores, the dull are the ones with high scores. Yes. The iron started with 140 rats and 42 rats, and the distribution of their intelligence scores is same as the number of errors. It's getting the following.
So the error is not defined, right?
No, error means if, for example, if the rat goes to the target, then there is no error, otherwise there is error.
No, I think the rat can change his path if he went
Yeah,
wrong.
maybe it's counted like that. Otherwise, yeah, I don't know.
In
I
a
thought
single-
maybe error means
Yeah.
I defined it like that. No, it's not. It cannot be like that because in that case, maximum number of errors is 19, of course. No. But maybe this is the number of errors. Means, for example, like that. Maybe he should have gone the other way around. That is an error. It's not clear how the errors were defined or how the errors were found. So I was assuming, I didn't look at this graph carefully only now, I saw that it's 200. Yeah, but anyway, still the number of errors, large number of errors made by only a small number of animals because the height there is short with high number of errors. So this was the distribution. It's not a symmetrical one. This kind of shape is called skewed. Right? This kind of shape is called a skewed shape. The skewness is to the right. This smooth distribution. This side is called the tail of the distribution. Tail. So when the tail is to the right side, we call it right skewed. Or in a number line, this direction is the positive direction. In this direction is the negative direction. So for this kind of shape is also called positively skewed, positive skewness or right skewness. So what they did was after that they divided these rats into two groups. Took the rats with smaller number. They don't mention where the dividing line goes. Some rats with smaller number of errors were taken as one group. Rats with higher number of errors were taken as another group. Divided first of all into two groups. Dividing line is not clear in the problem in the book. But then they bred these animals within each group. Right? So bright ones are mated with more bright ones. They have new offspring and so on. They bred it for several generations. They actually did it for several generations, and after that they had altogether 85 in male bright group, and the other group had 68 male dull rats. Right? So male bright the generation came from that bright rats. The other one came from male dull rats. Right? So if there is a real intelligence factor, as Pearson mentioned, these maize bright animals, if they are actually intelligent, so-called intelligent, they should be able to do more things better than the other ones. They are really intelligent, right? Intelligence is not only measured by how capable they are to run through the maze. Right? They should be able to intelligently do other things also. So, in order to check whether they are really intelligent for other things, actually they look at other activities with these animals too. So, they saw that after 7 generations, he produced 2 distinct strains, 85 of maize bright and 68 maize dark rats. Their test scores showed clear separation, right? At the beginning, of course. This was at the beginning. Now, after seven breedings, their test scores were they have clearly separated distributions, right? But this all the situations they were only running the maze, right? This is the ability to run the maze only, right? So intelligence for that factor was actually very high. Very low number of errors. That means intelligence factor was high for the bright ones. The other one was completely different. It has skewed but separated, almost separated except a small overlap. Right? So what they decided was actually, once you bred within these groups, you can have 2 generations, two separate groups who are completely different in terms of the ability to run the maze. But the question was really whether that ability measures their intelligence. Right? So in order to check whether what they did was, however, the maize bright rats did not outperform maize dull rats on other measures of intelligence, such as distinguishing shapes or light intensities. Right? If they were really intelligent, so-called intelligence, these people, the bright ones, should be able to do better in the other activities also than the other one. But they didn't find that kind of distinction in terms of the other activities. So that was actually enough to negate the Pearson's theory, right? Refuse Pearson's theory. If, as Pearson said, there is an intelligence factor, these so-called intelligent with respect to one activity should be intelligent with respect to some other activities as well. Maybe not for all. Like people also, they are intelligent, but they are intelligent with respect to certain type of activities, not for all activities. But they found out that if you consider any other activity, there is no difference, right, to say that there is an intelligence factor. So therefore, Spearman's general theory was refuted. It was not accepted. But this is funny actually. They found out that these maize bright rats had some other special property, and maize dull rats had some special property. That means maize bright rats were introverted and maladjusted to the society. Those and the other ones were completely different. They were more sociable. Right? Maybe that is also true for people. I don't know. So that they were trying to create this so-called intelligent generation and not intelligent generation. But when they are doing that, actually what happened was not really creating intelligent one, so-called generally intelligent, but of course with that breeding some other property develop as well, right? So some kind of maybe genetical one which is related to some other factor which is not related to the intelligence, right? So social ability, for example, was maybe related to maze brightness, right? Being able to go through this maze may be probably somehow related to social ability gene, maybe. That's what has happened. Right. So actually that is the end of this chapter as far as the book is concerned. So what we discussed was actually, okay, first of all we discussed the variables, type of variables. That was discussed because the type of variables classification is important, especially not only when you are deciding graphs, later on when you decide in different types of analysis also, type of variables is important. And then we didn't look at any graphs which is suitable for qualitative ones. The book doesn't talk about that. Here we only talk about special graph called the histogram, which is mainly suitable for continuous data, continuous variables. And then we discussed two examples particularly where the histogram was useful. Right. So we continue. Any question up to now? Do you read the book usually?
Yes.
Yeah. How do you find the book? Is it readable or good?
Readable.
I sometimes find the presentations and the order is somewhat difficult to understand. For example, when I read it first, I was not able to understand why these two particular examples were under histogram. But only when you read it several times, I understood, okay, this was they wanted to show some uses. They don't specifically mention like that, no. They just put two examples and they talk about these things. But they put it under histogram probably. Histogram is the one which helps to identify these things here, so that maybe that is the reason to put it under histogram. Okay, so we have a few more minutes. I will start this one. The next one is average and standard deviation. Average and standard deviation. So we saw that histogram is one way to kind of summarize the data. We can have a very large data set, but then you can put it into one simple graph. It shows a lot of things, right? Generally how the different values are possibilities, right? Frequencies or the percentages are which values have high possibilities and which values have low possibilities, the frequencies or the percentages, right? And thereby you can classify the distributions as, for example, symmetric or skewed generally. When it is skewed, we usually look at whether it's skewed to the right or to the left, right? Positively skewed or negatively skewed and so on. So it's a kind of a summarizing method. But sometimes we can give the same idea about the whole histogram without a graph, but by looking at some numbers. What the histogram tells us can be almost the same thing can be told by numbers sometimes. For example, when the distribution of the histogram is kind of symmetric, that can be described by maybe two numbers generally. By telling where the middle of the distribution is, how much spread is there roughly. Will give you some idea, not exactly the shape, but it can give you most of the information in the histogram. So it's numbers can summarize the data further, right? In some situations, for example, if the distribution is skewed, for example, two numbers is not enough. Right? It doesn't talk about the skewness, right? Whether there is a skewness or not cannot be looked at by looking at the center and the spread only, right? So whether it is tilted to one side or not, we have to mention by a number in that case. If it is tilted to one direction, whether it's positively tilted or negatively tilted has to be included into that number so that you will be able to recognize it. Right? How much the tail is, whether the tail is going to be like this or whether the tail is going to be like this. Right? How much the skewness should be represented by the noun. Right? So in that kind of situation, if the distribution is not symmetric, you may need more numbers to summarize. So usually we actually look at several numbers. We call them number summary. Right? Sometimes people look at some characteristics, right? The center, where the center of the distribution is. That when you tell about that, you have some picture in the mind. How much spread in the distribution? Some way to measure the spread. And then how much skewness? Right? So there is a characteristic called skewness, and we are able to measure it somehow. There's another property called kurtosis. Right? That again talks about the tail. It tells you about the tail and also the peak. Right? Both descriptions are inserted in the kurtosis. Right? So those are the four main characteristics that people use to describe a distribution. It's like describing a person, right? When you describe a person, you can describe it by telling how tall he is, how fat he is, and so on, right? His skin color, hair style, and so on. So few features. Similarly, when you describe a data set or a distribution, usually people talk about the center, the spread, and the skewness and the kurtosis. But in the book, actually, they have discussed only two things, that is the center and the spread. Right? So, mainly, in order to describe the center, people use different types of measures depending on the situation. Different types. In some situations, some measures describe the center better than some other measures. So the book actually mainly talks about one measure, that is called the average. That's what they say. But to me actually, average is not a single quantity. Average is a general idea. But according to the book actually, what they mean by average is the usual arithmetic mean. Arithmetic mean. That's what they mean by average. But to my understanding, average, generally when you say average, it can be the mean, or it can be median, or it can be mode, like that. That's my understanding was. But in the book, mainly they use the word average. I don't know why. For the arithmetic mean. So I have added one or two sentences describing that. So here, for example, you see several smooth type of histograms. If you have kind of a symmetric one like this, then probably the center and the spread will be enough to describe that. But if you have skewed, positively skewed or negatively skewed, center and spread is not enough to describe that. You need some measure of skewness, and also how much is the peak. This is more peaked than this one. Right? So in order to describe the peak also, we need some other characteristics. Right? And even with those four, sometimes you may not be able to describe a distribution like this. When you have several peaks, you may not be able to describe it with four measures. You need more measures like that. But most of the times, in practice, you will have situations where four characteristics is enough, most of the times. Rarely you will have this kind of ones. This kind of ones will be the shape of histogram roughly when you have a mixture of two populations. Right? For example, if you say, consider the height of a gender randomly selected person, that person can be a male or female. But in the population, we know that the height distribution of males is different from height distribution of females. Right? So if you combine them together and look at the distribution of heights, other than considering distribution of female heights and male heights, then you might have a distribution like this, or something like that. Not like this, but two peaks right? Two model, bimodal, we say. Right? In that kind of situation, probably 4 characteristics is not enough. Right. But here I mentioned that often even more drastic summary or strong reduction of simplification is possible than the histogram. So you can use center or the spread. Right. So if you have now, this is actually actual situation. There are another example for bimodal situation. If you consider the distribution of surface area of Earth by elevation, right? If you consider a small area, there is certain elevation, right? So for that area, there is one value for the elevation. Another area, there is elevation for that. So if you consider the whole Earth, different surfaces have different elevations, right? Sea level elevation is 0, right? So there is a vast area with that sea level. So that number 0 will occur large number of times if you consider like that. So if you consider the whole Earth with respect to the elevation, you will get this kind of graph. Histogram. Can you explain how you get it like that? Zero will be obtained, for example,
Sea level.
for the sea level. So it's not that much. For example, if you consider 0, for example, small area like this. So what are these then? Sea level means this is the shore area, right? Shore. But in the sea, there are areas where it's very deep. So those areas are these areas. This is only the shore area. 0 means that area. Sea level means that. So then there can be mountains, right? High levels. These are in kilometers, right? 2 kilometers. So, but the areas with the 2 kilometers height is very small, or very, very small here. That means height is small. Right? So you will have that kind of picture. But this kind of picture cannot be explained using media, the center and the spread at all. Right? If you just talk about the center will be roughly somewhere here, and spread will be somewhere here. But then you will not see, you will not pick up the two modes in that case. You will just think that even if with one mode you can have the same thing. So you will completely miss this picture. Right? Okay. So therefore, sometimes just 2 measures is enough, sometimes 2 measures is not enough, sometimes even 4 is not enough. So the word average is a very loose term that I mentioned, as I mentioned. Everyday life, usually we talk about this means several meanings. This has several meanings according to the situation. Right? Some people use the word average to mean different things in different situations. In the general day-to-day life. Right? I have given 3 examples. The average test score of 30 students might be reported as 75. So if somebody says for this class average score for these 30 students 75, that person usually means arithmetic mean. That's what they mean by average in that case. If somebody says the average monthly household income in a village of 200 households might be 125,000, that may not be the average, arithmetic mean. That probably most of the time that in the median, right? Roughly 50% of the people have this less than this, roughly the other 50% have more than that. Right? This can be arithmetic mean also, but most of the times it's a median, because if you actually calculate the mean might be larger than that. Why?
People who burn a lot.
There are very few, maybe very rich people in a village or town or something. Right? So because of those people, the mean can be quite high, because when you calculate the mean, you add up all the numbers. No? So when you add even one or two very high numbers, mean will be going to that side. So usually, therefore, a variable like income mean can be higher. generally mean will not give you a good idea about the so-called average. Right. It's inflated by those very large but few numbers. Right. So in that case, mostly they mean by average when they talk about this the median. Right. If a shoes sales store says that the average shoe size sold in the store is say size 9, that definitely is not the arithmetic average. Arithmetic mean nobody just count at the number these things and then find out. These are just day-to-day life, right? Most of the times they mean most of the shoes that are sold are going to be size 9. That's what they mean by average. The mode. Right? So you can see that in these three situations, the average mean three different things. Arithmetic mean, median or mode. But in this book, average means arithmetic mean. So you have to understand. And when I actually got the help from AI says also in statistics, most of the times average means arithmetic mean. Right. So these are very simple. You know how to find out the arithmetic mean when you have a list of numbers. Right? You just add the numbers and divide by the number of numbers. If you have a simple frequency table like this, right? For each possible value you have a row, and for each possible value you have a frequency, and then maybe a percentage or unit frequency. Then how do you find out the mean? You can still imagine that you can create if you want the list, right? So that means you have n1 number of x1s, n2 number of x2s, and so on. So therefore you can still do the same thing. You have to get the total, that is you have to multiply x1 by n1, x2 by n2, k by nk, and then add them up and divide by the total frequency. Right? So that's how you calculate sum of ni xi values divided by sum of ni values. Right? So if sum of ni is equal to n, this is the one. Right? But that can be written in terms of the relative frequency also, because this ni divided by n is the relative frequency for each, so that I denote by ri. So therefore you can write down that as sum of ri xi also, ri xi. And you can see that actually this is actually a weighted average. This is a weighted average of xi's. Here the weights are ni values. This is a sum of ni. This is what weighted average is. For each entry you have a weight and then divide by the total weight. Right? And this is also a weighted average because you know that sum of ri is equal to 1. Right? So if you consider ri as a weight, this term is this one, but then it is like dividing by sum of ri, because sum of ri is equal to 1. So you can consider the average of this distribution as a weighted average in this way, or weighted average as this way. So this is an example. The product is sold to this. We looked at this example earlier also. So we have this frequency distribution. So you can calculate the average like this. It's very simple. I don't have to take time. It's very clear. Right. So how do you find out the average if you have a group frequency distribution? Right. If you don't have the original data, if you are given only a group frequency distribution, you are given the class intervals, and then from those you can find out the midpoints if you want. Suppose you are given the frequencies, right? Usually you will have this and this only. From those you can get the midpoints and width if you want. If you have group frequency distributions, you cannot do anything. You cannot get the original data. You have to make some assumption. Right? So, for example, if you have n1 observations in this group, you generally assume that it is similar to having n1 times the middle value. Right? That's one assumption that you can make. Right? You represent all any number in this interval by the middle number, and then having n1 numbers in this interval, you assume to have be the same as middle number appearing n1 times. So that's the best or the most simple assumption you can make. So once you make that assumption, you can do the same thing that you did earlier. So midpoint times frequency, midpoint times frequency, midpoint times frequency. So ni times mi divided by sum of n will be the average. But if you want, you can write down it in terms of, for example, densities also. So I have shown you how to do that. It's very simple. I call it here the relative frequency density. Right? If you want, you can write down by percentage. Right? Percentage will be just this divided by multiplied by 100. Right? So you can write down it in terms of these d densities and width and middle values, or you can write down in terms of the areas in the histogram. Right? di times wi will be the area of ith column. Di is the height, and then wi is the weight, and width, and therefore di wi will be the area. So you can write down like that. And this again can be written as a weighted average if you want, because the total area, sum of ai will be equal to 1. Total area is equal to 1, so they are the same as that. So you can write down the mean in any of these ways. I think that is enough, right? We can discuss these things later. I'm a little bit, my throat is a bit troubling me.
Share something.
Yeah, I think that's